Let's do some sound check first. Can you say Streichholzschächtelchen?
Streichholzschächtelchen.
That was good. You have a good German pronunciation. I approve.
Well, that's,
Hei sann, og gratulerer med den direkte observasjonen av gravitasjonsbølger. Vet du ikke helt hva det er, eller klarer du ikke helt å føle på deg hvorfor dette er en så stor begivenhet? Ikke jeg heller, så jeg tenkte jeg skulle spørre noen. Og den personen jeg skal spørre, jobber der.
Knock, knock.
Hi.
Fan. So, first of all, gravitational waves, I will call them G waves. Sounds cooler. Is that okay?
That's fine, yeah. Well, you could think about gravitational waves or G waves as essentially ripples in space, right? Periodic ripples in space which expand with the speed of light.
Okay, what does that mean? What?
Well, space or space-time, you could put coordinates at each point, like at this table and over there. And then you look as function of time how these points move relatively to each other. And if the gravitational wave would go through, then you would see that actually the distance between different points would change periodically, and it would stretch in one direction and squeeze in the other one.
Okay, so if space together with the object is stretched, how is it even possible to observe it? How do you know it's real?
Well, it's a good question. It was for a long time disputed if these gravitational waves exist, and even Einstein wrote a paper where he proved that they don't exist.
Oh.
Right. And probably people were convinced only in 1957, that gravitational waves exist by a very simple argument. So if you think you have a kind of rod of metal, the gravitational wave goes through, and then it tries to stretch the atoms. Thereby it transports energy, produces heat in this rod. And this means that the gravitational wave, if it transports energy, it has to be real.
Oh. So how did we observe the G waves, just like Einstein said, or?
Well, this was a different experimental setup. It was a laser interferometer.
Laser.
So you have a laser which emits light of a definite wavelength.
Yeah.
Then you have a beam splitter which splits the beam in two parts.
Okay.
And then there are two mirrors which reflect them back. They go through the beam splitter and again to a sensor.
Yeah.
And the idea is that one splits the distances such that one has destructive interference.
Okay.
So one says, for example, one beam travels 1,000 wavelengths, and the other beam travels 1,000 and a half wavelength, such that with destructive interference one has zero intensity at the sensor.
Oh, that sounds boring.
Right, so it should be boring until the gravitational wave goes through the experiment. Then the space between the mirrors is deformed, and the path the laser beam has to travel is changed, and one has not destructive interference anymore completely. So this means that the intensity one measures in the sensor will be blinking with the period of the gravitational wave.
So won't the laser wavelength stretch in the same way as space? So the distance would be the same.
You have to do the calculation, and then you see that the stretch of the wavelength is much less important than the stretch of the distance between the two mirrors. And so in this case, this 1,000 wavelengths became then 1,000.000001 wavelengths, and you could see this change in intensity.
Could you actually see the light with your naked eye? Or?
Probably you could see the light, but you could not see the intensity change, which is so tiny.
How quickly would this blinking occur?
Change? I mean, the period of the gravitational wave was at the beginning 50 hertz and then something like 200 hertz.
If we were to observe the experiment, we would just see some light.
Smeared
You
out.
won't see a blinking. but it's actually there. It's just blinking at 200 times per second. Okay, so G waves directly observed. Good, like thumbs up. But why are people so excited? Actually, I can't personally feel the excitement. Not in the way that with the Higgs boson, I knew that it was a big discovery.